All right, so in this final chapter of Physics 4B for this semester, we're covering, as at least as one topic in this chapter, a displacement current, right? Maxwell's displacement current. And so what we see here is a voltage source, right? An AC voltage source that's varying in time at a frequency of 115 radians per second. And so that's pushing current or pushing conduction electrons one way around this circuit and then back the other direction, right? It's alternating the current. And that means that not only are conduction electrons moving in the wire, but they're also moving in between these parallel plates, right? These circular parallel plates in this capacitor. These plates are indeed parallel. They're of the same cross-sectional area and they're separated by a distance d, right? We don't know that separation distance. We'll actually need to find that in part C, but we do know a radius, and they actually do provide a displacement current value, 9.1 microamps. Okay, so part A is asking us to find the maximum value of the current I in the circuit. That's not necessarily the same as the displacement current, right? The displacement current is really, it is a current. It's a type of current, but it's a current where the electric field magnitude is changing, okay? And that is occurring inside this parallel plate capacitor, right? Specifically on the plates and inside the space between. So in part A, the maximum value of current I, that has to be the same as the displacement current. And that comes from simply conservation of charge, right? The same amount of charge has to be, well, in this section of the wire as in this section, right? Even though it's a capacitor, current can't necessarily build up and just simply stop. Right? If this voltage source is pushing charges onto this bottom plate, yes, they build up, but they're also transferred to the other plate, right, in the form of a current, the displacement current. Okay. So part A, the displacement current equals, we'll say, the maximum of both, is the same. Right? And that's the given 9.1 microamps. And again, this comes from conservation of charge. Part B wants us to find the maximum value for d phi dt, right? Where phi E is the electric flux, right? That goes back to Gauss's law. So in part B, d phi dt, right? That's the change in electric flux over time. Well, what's this change in flux? Well, that means that involves some area, that involves the electric field, obviously, and one of those must be changing in time, right? The area of these plates is constant, so that means that the electric field value has to be changing, right? And indeed, that should be apparent because the voltage source is changing in time. It's sine omega t. And voltage and electric field are intimately related, okay? So, part B, again, is fairly straightforward. Now that we have the displacement current, right, or actually we have it stated, we can find d phi dt. The definition of the displacement current is epsilon times d phi dt, right? We know that from Maxwell's equations. So we're simply solving for this expression d phi dt. Well, that's fairly straightforward. Divide by epsilon naught. We actually don't have to calculate the electric field magnitude or area quite yet, all right? Especially not since we know I and epsilon naught. So let's see, that's the 9.1, right, 6. Epsilon naught has a magnitude of 8.85 times 10 to the minus 12, I believe. And this gives us roughly, let's see here, a value of whoops, 10 times 10 to the 5th. Yeah. And the units are a little funky. Voltage times meters per second. Right, that's a little weird. That's because we have the numerator, right? The current is in, well, amps. And epsilon naught has units of farads per meter. And so from that, we get voltage times meter per second. Part C is where it gets a little bit interesting, okay? So in part C, we want to find the separation distance D, right, between both plates. We know the displacement current now. We have an overall value of d phi dt, but we don't know necessarily the electric field, right? It asks specifically for the maximum value. That's important. So let's write down again displacement current. Let's see, d phi dt. Okay. We have an expression for the voltage, okay, with this epsilon naught here, right, this script E as the maximum, right, epsilon maximum. So let's write this out a little bit. Okay, so we have d dt of the electric flux, remembering all the way back to Gauss's law, is actually the integral of E dot dA, right? So if we take a look up at the capacitor again, let's take a look at the bottom plate. I'm going to sketch that over here, okay? So let's say, for example, during some time the electric field is going up, right, from the bottom plate up towards the positive plate. The electric field vector is going straight up, right? That's perpendicular to the area or that face. Well, that's also the orientation of the area vector of the plate itself, right? That's always normal to the surface. So those two, E and A, are thus parallel to themselves. And so evaluating our integral down here, we have epsilon into dt. Let's see. Electric field magnitude, for right now, we'll just keep it as E, dotted with dA. Well, what's the magnitude of dA? Integral dA, more specifically, that's just A, the area. And since they're parallel, we have cosine of 0. That's the angle in between. That's just 1. Right? So far, so good. So now we can start breaking down E and A a little further. We have, well, actually, before I do that, which is changing, E or A? I've already mentioned that the area of these plates is remaining constant, so we can actually pull that out, out of the differential, and now we just have dE dt. Okay, we can write the electric field, let's do it up here, as, say, a voltage per distance. That's where our distance comes from. And then that's the distance in between the plates. Okay, so now this is ddt of the voltage over some distance. Keep in mind that's the maximum. Right? I guess I should write that. Let's see. Maximum. Okay. Well, that's just the coefficients. Let's bring the d out front because that's constant. And now we just have dv dt. Right? dv dt, well, that's the same thing as, actually, let me, epsilon max times sine omega t. All right. Take the derivative of this with respect to time. We get the following. Let's see, we have epsilon max omega and then cosine omega t. Okay. And so now, actually, sorry, back here, this is just V. I got a little bit ahead of myself. let's see. We want the maximum value, sorry, the separation distance. Okay. Separation distance, when that's ID, well, the separation distance will not change when the voltage changes, right? The voltage can be 0 at some time, and the separation distance will still be the same as when the voltage is maximum. So we can make our life easy and just take, well, when cosine is 1, right? When that cosine goes away. And so, well, we really just need the coefficients then. So solving this expression for D, right, rather this expression for D, right, we get D equals epsilon naught times A, epsilon max, omega, divided by the displacement current. Okay? Plugging in all of these values, we should get 8.85 times 10 to the minus 12. The area is the area of the entire plate, which is, well, the radius is given. So that's simply pi times 0.29, since it's 29 centimeters. That squared, pi r squared, times the maximum voltage, which is the 220 volts, times the frequency, the angular frequency to be exact, of 115, all over the displacement current value, which way back in part A was 9.1, times 10 to the minus 6, and we should get a value of, check my notes, should get a value of 6.5 times 10 to the minus 3 meters, which is not that far, right? That's pretty darn close, only 6.5 millimeters. So that's part C, right? We kind of dissected the electric flux expression a little bit, right? To extract the voltage and the distance, okay? So that was part C. Part D is we're finding the maximum value of the magnitude of the magnetic field in between the plates at some distance r, which is less than the maximum radius. So now let me go to this page. Part D, we want to find, this is not to scale, but if that's the upper plate, that's the lower plate, we want to find when the electric field is, say, going from bottom to top. How do I draw this? Something like this. What's the magnetic field going around a small circle at that radius from the central axis? We can call that distance r.